Hello and welcome to the video lecture on chemistry of heterocycles, semester 5, paper CC12. So today we are going to talk about heterocycles. This is the first video lecture on this series. So let's first define what a heterocyclic compound means. UPAC definition of heterocycle is cyclic compounds that has ring member atoms of at least two different elements. অর্থাৎ একটা cyclic compound যদি রিং এলিমেন্ট গুলোর মধ্যে অ্যাটলিস্ট দু রকমের এলিমেন্ট থাকে তাহলে তাকেই হেটেরোসাইক্লিক কম্পাউন্ড বলে। যেমন ফর এক্সাম্পল আমি এখানে তিনটে heterocyclic compounded structure এঁকেছি। The first one is quinoline. As you can see, it's a bicyclic compound. One of the cycles contain nitrogen along with carbons. The second one is 1,2-thiazole. That means it's a 5-membered ring, has three different atoms, sulfur আছে, nitrogen আছে, carbon আছে. And the other is a bicyclo-3,3,1 tetrasiloxane, where we have oxygen and silicon making up the bicyclic system. Usually, organic chemistry te আমরা কার্বোসাইক্লিক কম্পাউন্ডস এর থেকে ডিফারেন্ট হিসেবে হেটেরোসাইক্লিক কম্পাউন্ডদেরকে ডিফাইন করি। কার্বোসাইক্লিক কম্পাউন্ড হচ্ছে যে ধরনের কম্পাউন্ডগুলোতে কেবলমাত্র কার্বন থাকে, রিং এলিমেন্ট হিসেবে কেবলমাত্র কার্বন থাকে, আর সেই কার্বনের সঙ্গে যদি অন্য কোনো এলিমেন্টকে আমরা দিয়ে দিই তাহলে তাকে আমরা হেটেরোসাইক্লিক কম্পাউন্ড বলি। থার্ড যে এক্সাম্পলটা দেওয়া হয়েছে, যেমন এই বাইসাইক্লো টেট্রাসিলক্সেন, সেখানে বোঝা যাচ্ছে যে এটা বেসিক্যালি কোনো ইনঅর্গানিক এলিমেন্ট দিয়ে তৈরি, অর্থাৎ সিলিকন, অক্সিজেন, এই ধরনের এলিমেন্ট দিয়ে তৈরি। অতএব ইউ ক্যান কল দিস থিং আ ইনঅর্গানিক heterocycle. But in most cases, there are carbons along with other heteroatoms like sulfur, nitrogen, oxygen, etc. We are concentrated on mostly this type of heterocycles. Heterocyclic compounds তাদেরকে যদি একটা গ্রুপ অফ বা ক্লাস অফ কম্পাউন্ডস হিসেবে ধরা যায় তাহলে তাদেরকে দুটো ব্রড এরিয়াতে ভাগ করা হয়। একটা হচ্ছে অ্যারোমেটিক and the other is non-aromatic. Aromatic heterocyclic compound example হচ্ছে furan এবং pyridine, a 5-membered ring with one oxygen heteroatom and all sp2 carbons. Therefore, there are two double bonds, and the pyridine molecule has one nitrogen and 5 carbon atoms with 3 double bonds. So immediately it is apparent যে অক্সিজেনের দুটো লোন পেয়ারের মধ্যে একটা লোন পেয়ার has to be part of the aromatic 6-electron system, whereas in pyridine the nitrogen lone pair is not part of the 6pi electron system because it already has 3 double bonds. Our second যে ক্লাসটা আছে সেটা হচ্ছে non-aromatic heterocycle. For example, tetrahydrofuran, which is extensively used as a solvent. That's a cyclic ether. It's the tetrahydro derivative of furan. So if you add 4 hydrogen atoms across the 4 carbon ring carbons of furan, you get tetrahydrofuran. Then we have pyridine, which is the hydrogenated form of pyridine. The second molecule here is dihydrofuran 2,3-H-O. That means we have a carbonyl here. It's a intramolecular ester that is a lactone. This one here is dihydrofuran 2,5-dione. That's anhydride. This is an amide by pyridine 2,1, which is a secondary amide. Or you could have 1,2,3,4 tetrahydropyridine. That means if you hydrogenate 2 out of the 3 double bonds of pyridine, then you get an cyclic enamine derivative, which is this one. Amader presently discussion would be concerned with aromatic heterocycles with one heteroatom. এবং তাদের মধ্যে আমরা স্পেসিফিক্যালি ডিসকাস করব monocyclic সিস্টেমের মধ্যে furan, pyrrole is called 1H pyrrole because the nitrogen over hydrogen আছে, but most of the times we will ignore this 1H and simply call this pyrrole, and also we will discuss pyridine. In bicyclic system you have indole, which is also officially known as 1H indole, a benzene ring fused with a pyrrole moiety, a quinoline, which is a benzene ring fused with pyridine, so that the pyridine nitrogen is right next to the benzene ring fusion. And if we fuse the pyridine ring in such a way যে নাইট্রোজেনটা বেঞ্জিন রিং এর থেকে এক অ্যাটম দূরে থাকবে, which is an isomer of quinoline, so we call this isoquinoline. We have to discuss the synthesis, reactivity and chosen reactions of these six systems. Thiophene is presently not in our purview, but we will discuss it nonetheless when we discuss the general structure and properties of furan and pyrrole. So in general, the reactivity of these aromatic heterocycles, all of these are aromatic heterocycles, that should result from a combination of that is expected from typically from a aromatic system, as well as the heteroatom should also play a role, and therefore these combinations are usually more complex. And for the non-aromatic systems, it is not very different from the usual non-cyclic derivatives, which means that this can mostly behave as an anhydride, this will mostly behave as an enamine, this will mostly behave as a carboxamide, this will behave as a lactone, whereas furan or pyridine does not behave exactly like benzene, or because the presence of the nitrogen atom alters its reactivity, and furan also. So we take these issues one by one. So first যেটা আছে সেটা আমাদের হলো furan, pyrroles, এবং আমরা এইমাত্র বললাম যে thiophene we will also consider. So the general characteristics of these 5-membered heterocyclic compounds. The first thing that comes is because they are aromatic, we are concerned about the resonance energies, and these resonance energies have been measured. Experimentally, it is found that furan is the least aromatic of the lot, with only 17 kilocalorie per mole energy, whereas pyrrole is slightly more stable, resonance energy is 21. Thiophene is very stable, 29 kilocalorie per mole, and benzene, for comparison, we have tabulated here 36 kilocalorie per mole. So benzene has a resonance energy of 6 kcal per mole per ring element. Thiophene almost has 6 kcal per mole energy per ring element. কারণ এখানে 5টা অ্যাটম আছে, so 29 divided by 5 is almost 6. Benzene এর ক্ষেত্রে 36 divided by 6 is almost 6, but pyrrole and furan, they are significantly less aromatic. One of the very first rationalization that came for this was that sulfur is being less electronegative than both nitrogen and oxygen. Sulfur releases more electron to the ring. Because the lone pair on the heteroatom is part of the aromatic sextet, the aromaticity improves as the ability of donation of that lone pair increases, and therefore thiophene is more aromatic. So does sulfur really release more electron to the ring? What about other experimental evidences? If you take aromatic heterocyclic compound and compare it with its saturated analog, like tetrahydrofuran with furan, tetrahydrothiophene with thiophene, and pyrrolidine, which is the hydrogenated derivative, fully hydrogenated derivative of pyrrole, then you can compare their dipole moments. Before going there, let us see how the electron release from the heteroatom affects the dipole moment. So if Z is a heteroatom which has a lone pair of electron and it donates the electron pair onto the carbons making up the ring, then we have the following situation where the Z acquires a formal positive charge and one of the ring atoms gets a negative charge. Therefore, it's quite evident that if Z is an electronegative element, then the mu sigma for this system will be from the ring towards the heteroatom. And based upon these resonance structures, we can safely assume that the mu pi will be from the heteroatom to the ring. So by considering the minus I and plus R effect of Z, we can decide upon that mu sigma is like this way, which is the red colored arrow, and The mu pi is like that way, which is the blue colored. It stands to reason that greater the electron flow from the Z element to the ring, higher is the value of mu pi. And if the plus R effect is so overcoming compared to the minus I effect, then it may so happen that the overall dipole moment will be from the Z to the ring, and if the minus I effect is much greater, electron released by plus R effect is much lower, then the overall dipole moment will be from the ring to the heteroatom. Now, the electron delocalization that was proposed for sulfur, it suffers an immediate setback. That is because orbital size of the ring carbon and the ring oxygen or nitrogen, whatever you have, that matches. But sulfur, we have seen numerous examples in our studies in organic chemistry that sulfur does not overlap very well with carbon because of the orbital size mismatch. So probably this is not true. Let's check. The dipole moment of tetrahydrofuran is 1.68 dBi and from ring to the heteroatom, whereas for furan it is 0.71 dBi from ring to the heteroatom. So obviously the decrease of the overall mu is due to the mu pi, which is acting from heteroatom to the ring, and the difference is 0.97 dBi. For tetrahydrothiophene, because of the longer carbon sulfur bonds, despite having lower electronegativity difference between carbon and sulfur, the overall mu is higher compared to the tetrahydrofuran, 1.87 dBi. And for thiophene, it is 0.52 dBi. So the difference here is 1.35 dBi. And that difference here is 0.97 dBi. So greater the difference, lower is the mu pi. So you have a situation where the sulfur is actually donating a little bit of less electron compared to the oxygen, and that is expected. That is expected simply because our concern regarding the orbital mismatch between carbon and sulfur, that does not go down well as far as electron delocalization is concerned. And if you take into consideration pyrrolidine, which is not a good case, because unlike pyrrolidine is not flat and its NH bond is actually out of the plane of the two CN bonds. But still, some approximations may be done. For pyrrolidine, it is 1.57 dBi from heteroatom, from ring to the heteroatom. For pyrrole, remarkably, the dipole moment value is 1.84 dBi, but the direction has completely altered from the heteroatom to the ring. What does it signify? It signifies that mu pi is so strong that it has overcome this significant mu sigma, and now the electron flow is such that the dipole moment direction has completely altered. But again, this analogy between pyrrolidine and pyrrole and comparing that with furan, tetrahydrofuran, thiophene and tetrahydrothiophene is not exactly valid. But it gives us an approximate indication that nitrogen is a far better electron donor compared to oxygen or sulfur. That is expected because although the carbon sulfur orbitals suffer from size mismatch and oxygen being more electronegative than nitrogen, nitrogen has the best of the both worlds, which means nitrogen has greater electron releasing capacity due to their size matching as well as lower electronegativity compared to oxygen. So let's just say what about the calculated pi electron density for all these heterocyclic compounds? Here we have tabulated for the pyrrole, furan and thiophene, and the values at the pi electron density at C2, which is also called the alpha carbon, and C3 are tabulated because C2 is equivalent to C5 and C3 is equivalent to C4, you only need to note the two data. The thing is, you don't have to remember this, but look carefully at the electron density at the Z atom and the C2 and the C3. For Z is equal to NH, for Z is equal to O, and Z is equal to sulfur. In all the time, Z is more electron dense compared to carbon, which is expected. But Z, the pi electron density of Z is not exactly 2.0, and the C2, C3, they are not exactly 1.0. In comparison to benzene, where the pi electron density over all 6 carbon atoms is 1.000 up to 3 decimal. The C2 and C3 of Z is, when Z is equal to NH, that is pyrrole, is way higher compared to Z is equal to oxygen or Z is equal to sulfur. In fact, when Z is equal to sulfur, it is the least electron dense carbons of the three systems. All positions, that means C2, C3, they are more electron rich than benzene, and therefore we call these systems the pi excess heterocycle. So this observation implies that electron flow for thiophene from sulfur to the ring, it is compromised, and which is consistent with our previous remark that there exists a size mismatch and consequent loss of overlap between carbon and sulfur orbitals. These are the electrostatic potential maps of these systems. As you can see, the orange-red region implies higher electron density. Benzene is always there for comparison. For pyrrole, you can see the orange shade is much deeper compared to furan, as is evidenced here inside the ring. The heteroatom is sharing a little bit of more electron in furan, but for thiophene, you can see inside the ring there is practically very less orange shade, implying that electron flow from thiophene to the ring is not as good as in pyrrole or furan. Then the next question arrives: why is thiophene most aromatic? Because the resonance energy tells us that thiophene should be most aromatic, but we are getting the result that thiophene is not the best as far as electron sharing is concerned. So that question remains, because aromaticity should depend upon electron flow. If we are to rationalize that why the resonance energy of thiophene is higher, then we have to ask a fundamental question, a fundamentally different question. What does the resonance energy signify? Does it signify the electron flow, or does it depend only upon the electron flow? No, resonance energy actually tells you about the stability of the ring system. If the resonance energy is higher, then the ring is more stable. So why is thiophene more stable? One reason for thiophene's extra stability is obviously the larger size of sulfur, and that actually opens up the ring, the angles inside the ring, so that the ring strain is angle strain is little bit lower compared to that seen for pyrrole or furan. This is again the data where you have these bond angles tabulated. As you can see, for sulfur, which is implies the ring is thiophene, these angles are a little bit opened up, and the carbon heteroatom bond is significantly larger compared to carbon oxygen or carbon nitrogen bonds, and that will impart sort of stability. That is because angle strain is less. This should remind you of a situation that you have seen in neighboring group participation, whereas neutral sulfur was found to happily participate in intramolecular nucleophilic displacement and forming episulfonium ions, three-membered rings where one sulfur is positively charged. Neutral oxygen rarely participates or almost does not participate in three-membered ring formation. Only when the oxygen is negatively charged, that is, you have an alkoxide, the NGP can happen. That is because with NGP, using oxygen as the neighboring group, you will end up with an epoxide which is very strained, and therefore it is very difficult to form with neutral oxygen. We have OR or OH that does not act as a neighboring group. But with sulfur, with SR or SH, they react pretty well. That's because the three-membered ring containing the sulfur, positively charged sulfur, episulfonium, is much more stable compared to the three-membered ring containing a formally positive charged oxygen. So that should ring a bell that you have seen these things before. The second reason is sulfur has low-lying d orbitals, accessible d orbitals, which can overall offer a p-pi-d-pi conjugation to stabilize the system. If you draw the resonance canonical of thiophene, where sulfur has acquired a positive charge and the neighboring carbon has a negative charge, then you can also draw a third canonical where sulfur has expanded its octet by accommodating the lone pair of electrons from carbon into its vacant d orbital. Now that is a stabilization, which is a p-pi-d-pi conjugation. So our discussion with sulfur will not go any further because the system is stabilized. It has a greater resonance energy. When we discuss the reactions of furan and pyrrole, thiophene will keep popping up, but we will not focus on it per se because it's not in our syllabus. And we will not discuss any synthesis of thiophenes. We will be focusing from now on mostly on pyrrole and furan. And one of the consequences of the relatively lower resonance energy for furan and pyrrole is that these two 5-membered pi-XS heterocyclic compounds are more reactive than benzene, because as far as reaction of the aromatic system is concerned, most of the reactions disrupt the aromaticity. Therefore, higher the resonance energy, greater is the loss of the resonance energy, and greater is the difficulty to do the reaction. That means rate of the reaction should be slow. Vice versa, you have lower resonance energy associated with higher reactivity, and that is actually the case. And the second point is that because the resonance energy is low, aromatic character is also low, and as a result there are side reactivities that are expected for these systems. That means ignoring this double bond, this system can behave. For furan, it can behave as an enol ether. For pyrrole, it can behave as an enamine. And ignoring the heteroatom, these two conjugated double bonds can behave as a diene. There are plenty examples where this type of behavior is also shown. This is what I meant when I said that the reactivity of aromatic heterocyclic systems is not very straightforward. It is a combination of two factors. It shows aromatic reactivity as well as it has influence from the heteroatom. So the very first reaction that one chooses to do for aromatic system is aromatic electrophilic substitution. Because these systems are electron rich, as we have already said, the electron density on both alpha and beta carbons is higher than that seen in benzene. It promotes aromatic electrophilic substitution. And when you say SEAr reactions, it has a regioselectivity issue. That means where should the electrophile go? If you promote the attack at the C2, which is the alpha attack, then you have a resonance canonical where you have 3 canonicals. And for beta attack, there are 2 canonicals. These 2 blue colored canonicals are specially highlighted because these are especially stable, because they feature every element except hydrogen, they have their octet, while the black canonicals have at least 1 carbon lacking octet. So from our discussions in aromatic electrophilic substitution previously, we are immediately latching on to the idea that alpha attack should be kinetically faster compared to the butadiene, simply because the corresponding well-lined intermediate or sigma complex is much more stable. Now, when we consider the loss of the resonance energy, as we have just said, that greater the loss of the resonance energy, lower is the reactivity, and vice versa. Furan, being least aromatic of the lot, should be most reactive, followed by pyrrole, followed by thiophene, followed by benzene. Let us see whether our assumption holds up. So they have done a acyl derivative formation reaction. It's just a Friedel-Crafts type reaction. You can see that you do not need any sort of Lewis acid here, and only a mild temperature of 75 degrees is enough. These reactants are so reactive, and also in this case the acyl group is also very reactive, a good electrophile. Then the reaction is done without any intervention from a Lewis acid catalyst. Relative rate for trifluoroacetylation for these three systems is found to be, pyrrole is found to be most reactive, followed by furan, and thiophene is very less reactive. In a competitive type experiment where they have on one side of the carbonyl you have a furan ring, and one side of the carbonyl you have a thiophene ring. These rings are kind of deactivated because carbonyl is there, drawing away the electron density from the ring. And now they are doing basically a nitration reaction with acetyl nitrate, which is a mixed anhydride of acetic acid and nitric acid. Look at the temperature. It's minus 10 degrees centigrade. And then they are working up with pyridine. You will see why they are working up with pyridine. And then it is not the red thiophene ring where the reaction takes place, but it is the magenta colored furan ring where nitration has happened, which is again consistent with our previous observation that furan is more reactive than thiophene. So from these two observations, there can be many other examples. The order of reactivity that is found is not exactly what we are calculating or extrapolating, but very similar to that. Benzene is more reactive, less reactive than thiophene, which is less reactive than furan, and the least reactive of the lot is pyrrole. So the reactivity of pyrrole is much greater. Now, why is that? The loss of resonance energy for pyrrole should be a little bit more compared to furan. So it should be relatively less reactive, but it's actually significantly more reactive. That is rationalized in terms of the greater electron releasing ability of the neutral trivalent nitrogen and the greater stability of the positive charge on tetravalent nitrogen. And this is supported by the basicity order for the three saturated analogues. That means you have N-methyl pyrrole, N-methyl pyrrolidine, tetrahydrofuran, and tetrahydrothiophene. You are just measuring the basicity. So one way to measure basicity is to report the pK value of the conjugate acid, which is also known as the pKa. You can see that it is plus 10.4, it is minus 2.1, and it is minus 4.5. Greater the pKa, higher is the acid strength. That means the conjugate acid from this sulfur analog is the most acidic, and the conjugate acid from the nitrogen analog is the least acidic. Stronger the conjugate acid, weaker is the base. That means tetrahydrothiophene is the weakest of the lot, whereas N-methyl pyrrolidine is the strongest of the lot. What does it tell you? It tells you that the lone pair availability from nitrogen is far greater compared to oxygen or from sulfur. And as a result, if you go back to this thing which we highlighted when we are discussing this table, for Z is equal to NH, the ring carbons are most electron dense, because we told you that nitrogen has best of both worlds. Orbital size also matches, as well as nitrogen is less electronegative compared to oxygen, therefore has a little problem in relatively less difficulty in releasing electrons. And as it releases electrons, it activates the ring much more compared to when Z is equal to oxygen. One point we have to illustrate here, that although the N-methyl pyrrolidine ring, that's a typical, it shows a basicity of typical of a tertiary amine, R3N, and forms a corresponding quaternary ammonium salt, and so does pyrrole. If you protonate pyrrole, then you will get pyrrolidinium. But I'm sorry, for pyrrolidine, when you have protonation, you get pyrrolidinium. Pyrrole, on the other hand, is a much weaker base. And then there the question arises, where should you protonate pyrrole? You can protonate pyrrole on the C3, you can protonate pyrrole on the C2. As you know, 2H pyrrolium, that will be thermodynamically more stable with 3 canonicals. 3H pyrrolium will be slightly less stable with 2 canonicals. And if you choose to protonate pyrrole on the nitrogen, it is the 1H pyrrolium which is least stable, because you cannot show any resonance structures for it. But all these 3 conjugate acids, they have lost the aromaticity which was present in the conjugate base. Because the nitrogen lone pair, which I should have drawn here, is part of the aromatic sextet, it is exceedingly difficult to share this nitrogen with something external. If an H plus comes, it's very difficult to protonate pyrrole, because the lone pair is part of the aromatic ring. And out of the 3 situations, Monder Bhalo or best of the worst is this one, because it has 3 canonicals. But unlike pyrrole, for pyrrolidine, you don't have any aromaticity tying up this lone pair, and it is completely available, and therefore pyrrolidine can happily act as a base, whereas pyrrole is a very, very weak base. The corresponding conjugate acids pK is only minus 3.8. Let's move on to reactions. We are not going to discuss each and every reaction with its mechanism. The mechanisms are fairly similar with that seen for benzene rings or benzene derivatives. But we will discuss classes of reactions. You can do Friedel-Crafts acylation, where you are introducing a acyl group. Just mixing pyrrole with acetic anhydride will do. A little bit of Lewis acid in acetic acid medium will also achieve the reaction for furan. Diazo-coupling reaction, very, very good reaction, and you know that if the ring is not activated sufficiently, then diazonium ion, which is a weak electrophile that does not couple, it does couple with the pyrrole ring very efficiently, either on one side or from the both side. If you do the reaction in presence of sodium acetate, then you get the diazo-coupling on one carbon on one alpha position, and if you do that in presence of a slightly stronger base, you can have 2 diazoniums incorporating themselves at 2 alpha positions. Here we have a Vilsmeier formylation reaction on both furan and pyrrole. You should remember how the Vilsmeier electrophile is generated inside the reaction medium with N,N-dimethyl formamide and for POCl3. Take it as an exercise to find out whether you remember that. Halogenation, you can see that halogenation is done at minus 5 degrees centigrade, and with the more reactive system pyrrole, it is done at minus 78 degrees centigrade, and not even with halogen. They are doing it with N-bromosuccinimide, which is a source of Br+, or introducing chlorine with sulfuryl chloride, SO2Cl2. So multiple halogenation is often a menace, which to minimize that we have to keep the temperatures low. Nitration, typical nitrating mixture is absolutely not okay. You have to use acetyl nitrate, which is generated in situ by HNO3 acetic anhydride. Temperature is minus 10 degrees centigrade, whereas for nitration of furan, you are using a source of NO2 plus directly, nitronium fluoroborate, fluoroborate being the non-nucleophilic, non-basic counter ion, spectator ion. For sulfonation, you are using not sulfuric acid, but SO3 transferring agent, which is basically pyridine sulfur trioxide complex, generating sulfonated furan or sulfonated pyrrole along with the pyridinium, which is then worked up with dilute acid. So all these 6 panels of reactions should immediately tell you that the usual electrophilic reagents used for benzene ring is no longer valid here. These systems are exceedingly reactive because they are pi-axis heterocycles, and for that their higher reactivity allows us to use much milder versions. And we will also see that these rings are very sensitive towards protic acids as well, and therefore the use of the usual reagents like nitrating mixture, etc., is out of the question. If you do reactions with those reagents on these systems, instead of the desired electrophilic substitution, you will get side reactions so overwhelming that it will not lead to any fruitful conclusion. Now let's check uh, the alpha attack, the preference for alpha attack for the furan. But before going there, this slide should at least come after this slide, or you could actually directly go for this slide. Let's discuss that. So alpha attack is more preferred compared to beta attack. There is no issue with that. 3 canonicals for alpha attack, 2 canonicals for beta attack. A series of reactions are done on 3 different systems to demonstrate that the alpha beta ratio for furan is highest. In all cases, in all the reactions, the alpha beta ratio is highest. For thiophene, it is a little bit low. For pyrrole, it is the lowest of the number. That means pyrrole has little preference between the alpha and beta attack, whereas furan prefers the alpha attack very much. So why is that? Well, that is because the sigma complexes that are formed from the beta attack that rely more on electron release from heteroatom than does the sigma complexes that are formed from the alpha attack. What do I mean by this statement? When you have alpha attack, you have 3 canonicals, out of which there are 2 canonicals where the positive charge is not placed on the heteroatom. On one canonical, you have the positively charged heteroatom. Let us call this thing X. And these magenta colored resonance canonicals demonstrate that for alpha attack, you have an allylic conjugation. For beta attack, on the other hand, you have one canonical where the positive charge is on carbon, but there is no allylic conjugation. And the next canonical, you have the blue canonical where the heteroatom is forced to share the positive charge. Now, oxygen, being the more electronegative element, is reluctant to share its positive charge. So although these blue canonicals are the major contributor because octet is filled, for oxygen their importance is a little bit low compared to the situation seen for furan and thiophene, for pyrrole and thiophene, particularly for pyrrole, because pyrrole has pyrrole has nitrogen has greater electron releasing ability. So what does this conclusion leads us to? If we have Z is equal to nitrogen, then this canonical is also contributing, those canonicals are also contributing, this one is also contributing, that one is also contributing. So we have a situation where you have competition between 3:2. Alpha is favored by 3, beta is favored by 2. But if you move on to oxygen and now decide that these canonicals contribution have been significantly compromised, then you have 2 versus 1, 2 for alpha and 1 for beta. Now if you think in terms of the ratio, 3 divided by 2 is 1.5. So the alpha is favored by a factor of 1.5, and this time for oxygen, for furan, you have 2 divided by 1, that is 2. So it is 2 times more favored, and here it is only 1.5 times favored. So that is one way of explaining this. The other alternative approach is to consider the sigma complexes as a whole, and as you can see, the sigma complex is stabilized here for the alpha attack. The stability order for the sigma complex is nitrogen greater than oxygen greater than sulfur, because nitrogen has more electron releasing ability. And for the sigma complex from beta attack, the stability order is nitrogen greater than sulfur greater than oxygen. This is deriving again from the same logic that oxygen does not want to share the positive charge, and for this system the carbocation will enjoy some sort of allylic conjugation, whereas for this system there is no allylic conjugation. Therefore for oxygen, it is the sigma complex stability order actually reverses. Here oxygen is greater than sulfur, here sulfur is greater than oxygen. Therefore it has a greater minus I effect, which destabilizes the neighboring positive charge. And when you are protonating or doing the electrophilic substitution at the alpha position, the positive charge initially formed is at this position. So you already have a canonical where the positive charge is away from the heteroatom. When it is oxygen, the minus I effect is greater compared to that of nitrogen, but positive charge is away from it. But for beta attack, there is no other option but to place the positive charge on the atom next to the heteroatom, carbon atom next to the heteroatom. So this heteroatom is drawing away the electron happily when Z is equal to oxygen, and you have a little bit of problem here. When it is sulfur, due to less electronegativity; when it is nitrogen, due to less electronegativity, these are comparatively more stable when Z is equal to oxygen. Therefore, the sigma complex from the beta attack, the order is nitrogen greater than sulfur greater than oxygen. For sigma complex from the alpha attack, nitrogen greater than oxygen greater than sulfur, which leads to the outcome that alpha attack is very much favored for oxygen, and oxygen particularly abhors, does not like, dislikes, has no willingness to form the beta attack sigma complex. And the third way of realizing this, that why it is the minimum for the, why it is the minimum, why the alpha beta preference is minimum for the alpha beta discrimination is minimum for the pyrrole ring, then we can say evoke the old principle of something which is more reactive is less selective. Although that does not hold true in all cases, but this time it will work nicely, because electron density among the ring atoms is highest for pyrrole, pyrrole being more reactive of the three systems, it is less selective, and therefore it chooses alpha as well as beta more or less in an equal fashion. Alpha is more favored, but beta is also selected. Furan, on the other hand, makes a discrimination and does not allow the beta reaction to proceed if alpha positions are available. You will get to see the overwhelming preference for the beta, for the alpha attack when Z is equal to oxygen in the following reactions. If you do aromatic electrophilic substitution on mono-substituted heterocyclic compounds, then there are two factors need to be considered: the effect of Z and its say in the regioselectivity, and the effect of the substituent that is already present. Here again you have to consider two things: if the substituent that is present is electron donating or electron withdrawing in nature, and then where the substituent is actually present. So we can have four different situations. We can have electron withdrawing group present in the ring. You can have electron releasing group present in the ring. You can have the electron withdrawing group at C2 as well as at C3. That means alpha and beta. And same thing with electron releasing group at C3 or beta, or C2 at alpha. So let's consider if the electron withdrawing group is at the C3, that is the beta position. With respect to this withdrawing group, the electrophile should be directed meta. Now it is very difficult to find out the meta position or ortho positions because this is not a benzene ring, but allowing for the convention of the next carbon attached to the ipso carbon being ortho and the next carbon being meta, you can say that this is a meta position with respect to this ipso carbon, and this one here is an ortho position with respect to the ipso carbon. So W will try to direct at these positions, and we know that Z has a tendency for the alpha attack, and particularly so when Z is equal to oxygen. So it is the alpha and meta position where the preferential substitution will take place. For example, if you take a furan system substituted with a CO2H at the one of the beta position, then it is the remote alpha position where the nitration takes place. Similarly here, it is the remote alpha position, that is the alpha and meta with respect to nitro, alpha with respect to nitrogen, the acylation has taken place. What about electron releasing group at C3? Obviously, it will now prefer these positions because these are the ortho positions where the reaction should take place. And this one is meta with respect to the R group, therefore it does not encourage particularly attack here. However, this position is alpha with respect to Z. This position being alpha with respect to Z as well as ortho with respect to R will undergo preferential reaction. Unless your incoming electrophile is extremely bulky or your R group is extremely bulky, the reactions will take place here. As you can see, you have a CH3 placed, which is a electron releasing group, not very bulky, formylation at the proximal alpha position, nitration at the proximal alpha position. Electron releasing group at C2. Now this will, lead to a direct conflict, because if you have W here, then this is ortho, this is meta. Meta is better for W. This alpha position being already blocked, if you are not talking about any ipso substitution, then this is the only alpha position that you have. But that is in fact para with respect to W. So Z wants to direct the electrophile here, but W discourages attack here, because if the electrophile attacks here, you get a positive charge on this carbon, and that's bad. So W wants to direct here, Z wants to direct here. If the effect of alpha directing ability of Z is greater than the meta directing ability of W, then you will have substitution at the alpha position, and that is exactly what is happening. You have a nitro group at one of the alpha positions. When Z is equal to NH, the major product nitration is here, so it is avoiding this alpha position and avoiding the sigma complex that generates a positive charge on this carbon. That's the major product. Again here you have COCH3 when Z is equal to NH, again nitration is here, not here. That's the major product. But when Z is equal to oxygen, for reasons already mentioned, alpha directing ability is sky high, and you have nitration at this position. That's the major product. In fact, that is the exclusive product in both cases. So that clearly and very nicely demonstrates what you are dealing with here. You are dealing with something which is extremely sensitive towards alpha attack. It does not care whether it has any other substituent present in any other positions of the ring. As long as it has a vacant alpha position, it will send the electrophile there. Electron releasing group at C2, that's very fine, no problem. This one is ortho but beta, this one is meta and beta, therefore that's the least preferred position, and that one is clearly the favorite position because it is alpha as well as para with respect to the R group. So you have CHO group introduced here, formylation taking place here. Okay, before concluding this, we will discuss one more reaction. Before concluding this video lecture, we will consider one more reaction. That reaction is functionalization of the beta position and functionalization of the N position of pyrroles. Because pyrrole has a preference for alpha attack, not as much preference as for furan, but still, if you are trying to synthesize something like this, 3-nitropyrrole or 3-bromopyrrole or 3-formyl pyrrole, it is not an easy task to do this reaction on free pyrrole, because if you do the reaction with nitration or bromination or formylation reaction on free pyrrole, then invariably it is the major product would be the ortho-functionalized pyrrole. To improve your yield of your target molecules, you will have to block these ortho not ortho, alpha positions from reacting. And you can do that by statically shielding these alpha positions so that the electrophile feels discouraged in attacking it. You can go for a silyl protecting group on nitrogen. So what you do is that you deprotonate this nitrogen. Pyrrole has a acidic hydrogen, and its NH bond is almost as acidic as an OH bond of an alcohol. Any sort of aliphatic amine, you have say pyrrolidine, the pK value is way higher. pK is 44. For aniline, it is like 30.6 because of the minus I and minus R effect of the ring. And for 2,4-dinitroaniline, you have electron withdrawing groups present in the ring, which lowers the pK to a almost manageable extent, and pyrrole has a pK very close to that because its conjugate base is resonance stabilized. Its NH bond is significantly more acidic compared to its saturated analog. So if you deploy a base like sodium hydride, then pyrrole will be deprotonated. Fine. So the pK value is 17.5. You get a deprotonation, and you then react it with a silicon electrophile, triisopropyl silyl chloride, nitrogen being the hard center, carbon being the soft center. This pyrrolyl anion will be ambident nucleophile. It will react with the hard silicon atom at the nitrogen, and therefore you have N-silylation. And because the silicon is loaded with these isopropyl groups, they statically discourage any sort of advance from any reagent at these alpha positions. And so when you do the nitration or the bromination or the formylation reactions, all this time the electrophiles are directed towards the beta position. Once you have done that, your job is only half done because you need to get rid of the nitrogen silicon bond and replace it with the nitrogen hydrogen bond. So silicon can be taken away from this nitrogen by offering a better reaction partner, that is tetrabutyl ammonium fluoride. Silicon fluorine bond is extremely strong, and you have seen this thing when we discussed the protecting group chemistry in last semester, where fluoride was being used to lure away silicon atoms from silyl ethers. This time also we are using the fluoride to take away the silicon and generate our target molecules. For N functionalizations, you need to generate the corresponding anion, otherwise it is difficult to react at N. You need to preserve the aromaticity while you are reacting at N. If you do the reaction on N on pyrrole, then the lone pair is part of the aromatic sextet, so therefore it will be tied up in the resonance and therefore it will not be donable. On the other hand, for the anion, the lone pair is one of the lone pair is not part of the aromatic sextet and it will react. So you can deprotonate it with sodium or potassium amide or n-butyl lithium or CH3 magnesium iodide, etc. In the last case, you have a covalent bond existing between nitrogen and magnesium, whereas for lithium, potassium and sodium derivatives, these are the more electropositive elements than magnesium. It exists as an ion, and therefore the reactivity is enhanced and the reaction preferentially takes place at the nitrogen center, provided your electrophile is such that it allows reaction with nitrogen. For CH3MgI or any Grignard that you have used to deprotonate the pyrrole derivative and form the magnesiopyrrole, if you do the electrophilic substitution, the nucleophilic displacement reaction in a polar medium like HMPA, then nitrogen can be functionalized. But if you use a less polar solvent, then it is not in functionalization, but the C2 and C3 functionalization that of the pyrrolyl magnesium derivative that you will see. Again, we have a potassium derivative forming here, and then treated with acetic anhydride, you get N-acetylation. Again, a potassiopyrrole, benzoyl chloride is reacting, you get N-benzylation. So N-acylation of potassiopyrrole is doable. N-alkylation of sodiopyrrole is doable. N-alkylation of magnesiopyrrole is also doable, provided you are using polar solvent like hexamethylene phosphate triamide or HMP. If you do the reaction is low polarity solvent where the ionic character is less, the covalent character is more pronounced, then the C2 and C3 functionalizations will take place. So this much for this installment of the series. Thank you for your patience, and I will be seeing you in the next one.